Right, let's see this. So what we will do, we'll try to uh, do aldehydes and ketones mainly in two parts. First is all about preparation reactions, then chemical reactions. Within the chemical reactions, we have reactions up to certain level. After that, there is one complete set of reactions which belong to a completely new category. Okay, so that we will read it as separate part. So let's start with this one first. Alkyl halides can be prepared from alkenes, not directly from alkanes. So alkenes on ozonolysis, we know that we can break the double bond, convert them into aldehydes in the presence of zinc and H2O. So this is reductive ozonolysis. So what we are doing is reductive ozonolysis. Okay, next. So you could notice this as an example. You break it, this part will become ketone, this part will become aldehyde. Okay. Alkynes can be prepared into aldehydes and ketones using mainly two reactions. One is HgSO4 and the other one is B2H6 or SiA2BH. This we have discussed recently. Okay. During the doubts, we discussed how the alkynes will react. Alkynes with HgSO4 will form a bridge compound, and thereafter water will always attack on the more substituted side, breaking the mercury bond. And then carbon has a double bond, will have sufficient electronegativity to break with mercury to give away Hg2 plus. And then from this minus charge of carbon, it takes H plus and convert into finally an enol form. So this enol will convert into a keto form. That's the reaction which you will notice for alkynes. Next, if at all I take SiA2BH, okay, secondary isoamyl boron hydride, we know that first you will get an alkynyl boron, and this alkynyl boron, when you react with peroxide, so this will be removed and OH will come into picture, which will convert into an aldehyde. Okay, so if you want ketones, you will go with HgSO4. If you want aldehyde, you go with SiA2BH. B2H6 is generally avoided for the fact that the aldehydes can again get reduced to alcohols. Okay. Next. If you want an aromatic aldehyde, then what will you do? See, benzene plus HCl plus CO, right? Sorry, here, HCl plus CO. This will turn into benzaldehyde, which we call it as Gattermann-Koch reaction. This is Gattermann-Koch reaction. Next, if you use instead of that HCnZnCl2 in the presence of HCl, this will be Gattermann reaction. These two reactions we have learned it earlier in benzene. Same reactions as as the reactions of benzene, where this will form an electrophile like this. HC double bond O plus. This is the electrophile. Here HC double bond NH with plus charge. This is the electrophile. Okay. So here EAS reaction will happen. Here EAS reaction will happen. Both via EAS mechanism, it would eventually give you benzaldehyde. If you want ketone, you do acylation. So you take acid chloride, react with AlCl3. You will get acyl groups, that is CH3C double bond O group. Benzene will attack on that carbon, converts into a keto form. Okay. Right. Next, if you have an alkyl halide, so that is if you have two chlorines here, you can react with aqueous NaOH, and you can make first, the mechanism could be as simple as having one chloride here and one OH here, and in the basic medium again OH minus can take H plus from here, creates an O minus and Cl minus. Internally this O minus can push remove out this Cl minus. That's how you can get a keto form. Done. This is from alkyl halides. Okay. Next, from Grignard's reagent, this we have learned as a part of reactions in alcohols. Grignard's reagent, generally when you take an carbonyl group, it will convert into an alcohol. But now we want carbonyl group. That means we want aldehydes and ketones. So then we will take acid chlorides of only one equivalent. Okay. So if I take one equivalent of RMGX, this R minus will attack, this Cl minus will go. Got it? That's how you will get a keto form. Same logic applies to ester also. This will attack, OCH3 minus will go. This is the first mole. Well, if you have a second mole also, it will again react with this ketone, converts into alcohol. Hmm? Next, if you have a cyanide, then R minus can attack on carbon, gets into this part. Now, because of C minus, there is not much of delta positive charge on carbon anymore. In fact, the group will repel any incoming RMGX. So if you have a second mole of RMGX also, it will not let attack this carbon. Therefore, no matter how much excess of RMGX you keep it, the reaction will stop here only. And thereafter, when you do hydrolysis, the bond will break from here, converts into keto bond. Okay, so that's how you can get a ketone from cyanide. If you remember, if you check it out, in this first case, we only require one equivalent. Here, you take one equivalent, two, three, or as much excess as possible, you will only end up getting a ketone. Okay. Next, if RMGX is reacted with carbon dioxide, it will become RCOO minus and it will lead to acid. So, well, from acids again you can reduce this to aldehydes, but well, this reaction is not for that. I have generally given you what are the typical reactions of RMGX. Okay, next. If you have an alkyl lithium and then you react with acid, now notice what we can get. R minus can attack on this C double bond O and convert that into a keto form. How would that happen? See, first this R minus will take H plus, convert into alkane, and you will get this compound. Okay, lithium salt, lithium carboxylate salt. And then the second mole of R minus can attack on this carbon. You will get O minus Li plus. So you will have O minus Li plus, O minus Li plus here. That on hydrolysis will convert into ketone. And this will convert into Li2O. Very important reaction, very specific in this case. So if you take any acid derivative, whether you take acid, whether you take ester, whether you take acid chloride, lithium, alkyl lithium will only give you ketones. Okay, beta, that will end up giving you ketones. So this is an important reaction, how you get it from alkyl lithium. So that means even if you take this acid and then react with this RLi, you should be able to end up with this ketone. Okay. Now notice how JE questions have been asked in this case. These two are very, very standard JE advanced questions. How they have asked. Check. Usually the question will always start with this one, which is acetoacetic ester. Okay. This is aceto. Clear? And this is acetic. This much. And this is an ester form. Isn't it? So that's why it is called acetoacetic ester. When you treat with NaOH, what would happen? Notice these two hydrogens are strongly acidic because it has withdrawing group on both ends. So this is called active methylene group. Such kind of groups are called active methylene group. This is active methylene group. And you get a negative charge there. And this will become a nucleophile to attack on RMGX if at all you are treating with with alkyl halide. So this R minus will attack, X minus will leave. So you will get an R substitution. Thereafter, if at all you hydrolyze it, on hydrolysis, you will be able to remove out this acid part, ester part, and convert that into an acid, because esters on hydrolysis will convert into acid and alcohol. Okay, so the other compound what you will have is ethanol. So ETOH will be separated out, and this part will convert into an acid. Okay, these type of acids are called beta keto acids. Mind you, at this alpha and beta position there is a keto group. At beta position there is a keto group with respect to this acid. Okay, that's why it is called beta keto acid. Now here is an important fact you need to remember for now, that beta keto acids, just on heating over the room temperature, we will be able to see this carbon dioxide going away, and the hydrogen left will get connected with this one, and that will convert into a keto form. Okay, so what did we do exactly? We took a beta keto ester. Acetoacetic ester is nothing but a beta keto ester. So this is a beta keto ester, and finally converted that into a desired form of ketone. Matlab, you can take R dash as per your convenience and as per your need, and accordingly you can get that particular keto form. Clear, beta? So I want you to check properly what exactly is the reaction happening here. Finished? Done, beta? Hmm. Check. Next one. This is also in a very similar kind of reaction here. See, we have ester here, we have an ester here, and between these two there is a active methylene group. Okay, this is an active methylene group here. So that when you treat with NH2 minus, what would happen? Okay, NH2 minus will take H plus from here, you will get minus charge here. That is the first thing. Right. Then you are treating with alkyl halide. So obviously this minus will go attack at this position, Br will leave. Done. This Br will leave here. And thereafter, correct, once it gets substituted, I am treating with NH2 minus again, because auric B hydrogen hai na beta. So there is one more hydrogen. So therefore, this NH2 minus will take away this H plus. You get negative charge, right? And internally we have one more alkyl halide. So this will go and attack that carbon, remove this bromine, makes the ring size into 6 carbon. Now you can see there is a 6 carbon ring size. Yeah. Now once you get the 6 carbon ring size, you are doing an hydrolysis now. So you are doing an hydrolysis. On hydrolysis, you'll get two acid groups now, because two alcohols will be departing. These two are ethanol forms here. So that is departing. Clear? And then we will get this form. Done. So once you get this, heating, again this is very similar to that of beta keto acid. So on heating that, we will be able to remove one carbon dioxide and left with acid part here. Okay, please check how the reaction is working. Any doubt here? This is just a hint at the bottom. You can see that if you have a beta diacids, this is alpha, this is beta. So this is beta diacids. Beta diacids, the carbon dioxide will be removed out of it. Okay. So therefore, that's how it will end up with one acid part.
Actually, the
Hmm?
hello,
Yes, beta.
the third step, the internally, the step before that, sorry, the H is again removed by NaNH2 only, right?
Yes,
And
beta. NaNH2.
then you
NH2 minus is
hydrolyze,
a base. It will remove H plus. Again, you get negative. So that negative internally is pushing onto the carbon to remove this Br.
and then hydrolysis, right?
After that, hydrolysis. Very good. So you will get these acids. And you can see diacids on heating will convert into COH with one CO2 coming out. Hmm? Okay. Finished? Right. Okay. See, in a very similar case, the second one here, you will should be able to notice a similar reaction here. Hmm? Done. Right. Check out same thing. OH minus with H plus minus charge will come. Again, here there is one side bromine, one side chlorine. So first bromine will be released out. Okay. One second. Right. So see this. So the minus charge would go attack on this carbon, remove one bromine part, and one more Cl is present on it. Okay. So now again there is one hydrogen beta. This hydrogen has to be removed. NH2 minus is used for it. Negative charge will come, and that will again attack on the carbons, fifth carbon. So that will go away. Cl will come out. So that's how we will get this cyclohexane group. Okay. So once you get this cyclohexane group here, hydrolysis is been done. So you'll get an acid here. So you can see this is alpha, this is beta. So beta keto acid is present. On heating, CO2 will go away. You will end up getting a keto form here. Okay. Clear on that? Right. Next. If you have a carbon dioxide and you react with pH minus, okay, so pH minus will attack on carbon. This will become O minus. So you'll get an acid group here. And then when you are reacting with CH3 lithium minus, you will get this as O minus and O minus. Then CH3 will attack on it. And that on hydrolysis will convert into keto form. Just now we have learned this preparation reaction from any RLI, From RLI, you will get that into keto form. Then afterwards, we have NaIO. NaIO is an iodoform reaction, right? This is an iodoform reaction. Now, due to iodoform reaction, this CH3 can be removed out, and you will get this as CHI3, okay? And which is a yellow color PPT. This is an yellow PPT. Done? Will you go ahead? Hmm. 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 Water. Right, beta. Check. Here we have this group now. This is also an active methylene group. So in this case, check out, there is a CH2 group here, and on treating with OH minus, so we will get this OH minus to take H plus from here. We will get a minus charge there. That minus will attack an alkyl halide, remove this X, so you will get R substitution. That on hydrolysis will remove this part, and this particular carbon will convert into an aldehyde. Okay. So this is another way of preparing aldehydes here. Clear, beta? Right. Next. What is the next reaction, which is Stephen's reduction? In Stephen's reduction, when you have a cyanide when you react with SnCl2 and HCl, okay? So first it will form an imine. It will form an imine here. So that means this triple bond will get added, one from nitrogen's lone pair, which will give you H plus, and then carbon will also get this H. See, basically SnCl2 is a SnCl2 with HCl. You can imagine it will start converting into SnCl2, SnCl4 plus two nascent hydrogens. This is what will happen. So these two nascent hydrogens are the ones which are getting added on to carbon and nitrogen. What makes up? Next here. Hmm. So now once you get this imine form, that imine on hydrolysis will take this H plus from here. So we'll get this as NH2 plus, and that makes this carbon to get positive charge. So that's where water can attack. You will get this OH, and NH2 will take away the H plus from that OH, as this lone pair will push here and remove this ammonia. So that's how you will get this aldehyde form. This is called Stephen's reduction, specifically used for making cyanides to convert into aldehydes. Clear? Right? Okay. See the next one. Now this is what we were. This is what I was talking about. Heating carboxylic acids. If you have, you know, alpha and beta here, so you can see this is beta keto acid. So when you have beta keto acids, as you heat, this CO2 will come out. Let me show you how that works. See, basically, if you have double bond O here and carboxylic acid's OH here and double bond O here, okay, then the lone pair from this oxygen will take away H plus. This bond will shift here, this bond will move here, and this will go into formation of pi bond. So in totality, you will see you will get this as OH and a double bond here, while carbon dioxide has been eliminated. And this in fact will turn into a keto form, and that's how we will get a keto group here. Done. So you can see from heating of carboxylic acids, you can get a keto form. Yeah. If you have a beta diacids, this is alpha and this is beta, and this is a beta diacid group. Then also on heating, similar mechanism will take place, and this time this side you will have an acid left. So therefore, acid will be left. This will come out as carbon dioxide. And decarboxylation will also happen when you have 6 carbons, right, with dioic acid. So if you have this COH and COH, which we call it as adipic acid, that also on heating, one of the CO2 will go away. You will get C minus here, which will attack here and converts into cyclic ketone. Okay. So this is pamelic acid, pamelic acid. So whether you take adipic or pamelic acid, both of them will give you cyclic ketones. Okay. So these are the heating effects of carboxylic acid. Well, these three you will again learn it back in carboxylic acid, but you can see this as a preparation of cyclic ketones, right? You can see this as a preparation of cyclic ketones. Got it? Any doubt, beta? 9th and 10th, please check. Here, can I go ahead?
Yes, sir.
Yeah, sir.
Right. See this. This was a previous year example. How this was asked. There are 4 cyanides back to back on 2 carbons. You did hydrolyze. On hydrolysis, what we should get, beta? You should get 4 acids here, correct? And then you started heating. On heating, because this is a beta diacid, एक CO2 हटा दो. This is beta dioic acid, another CO2, you can remove it out. And now you will have, at what is the position? Alpha, beta, at gamma. At gamma position, we have another acid. So if you have gamma diacids, then here dehydration will take place and converts that into an anhydride form. So you will get X as the anhydride form. And once you get an anhydride, remember reacting with benzene. क्या होगा बेटा? Acylation. ES Friedel-Crafts acylation. So you can get this part, reacted with AlCl3. This is how the benzene can attack. This bond can be removed out, and you would get this C double bond O connected to benzene. And then we will have COOH here, correct? Which we take it as Y in this case here. Thereafter, we are using HI and red phosphorus. Okay, so you can see we have HI and red phosphorus here, correct? Now I can extend this reaction. I mean, the question was only up to this point, but see how I can extend this reaction. Here, I can write this as, what if I react with Cr2O3, Al2O3 and heat? Okay. Next. So if you take Cr2O3 and Al2O3, one second. What happened? Go there. So if you take Cr2O3 and Al2O3, you will notice that this will undergo cyclization and converts into an aromatic group. Okay, that will convert into an aromatic group. So you can see these two and this one. So it will convert into an aromatic group here. So thus making into this particular form. So which is anthracene. So final product will be anthracene beta. Can you see the sequence, how it has been framed? Clear? Right. So follow the same thing for the second question now, which is very similar, but not ES reaction. But that there is no ES reaction here. But please try to follow the second question also in the same way. Please check. Right. Did you get this question? Second one. Should I explain?
Uh, can you explain the second step once again?
Second step. Okay. So first thing, A is all about getting the cyanides into hydrolysis, which will give you acids. Then you know that this is beta diacid. So remove one COH from here. Beta diacid, remove one COH from here. Beta diacid, remove one COH from here. So first three CO2 to वैसे ही चलेगा. Then there are two COOH group left. One is left here, one is left here. And when you have at this position, you know that on heating, it will form anhydride like this. So you can see here, there is an anhydride formation. And we are using 2 moles of CH3 MgBr, correct? And you know that when it comes to anhydride and ketones, ketones are more reactive. So first CH3 will attack here, it will become O minus. Correct. The second CH3 will attack here and this will become O minus, and one side it will become ketone, other side it will become acid part. Got it? And then again you are using CH3 lithium excess. Okay. So if you are using that excess, CH3 minus will attack here also. CH3 minus will attack here also. Hmm? And the acid group, when it attacks, it will end up at ketones. And at the keto group where it attacks, it will end up alcohols. Right? So here it will end up alcohols. So this part will become alcohol. This part will become alcohol. And this part will remain ketone. Right? That is the B part here. Thereafter, copper and heat. This we learned in alcohols. That is oxidation. When you take copper and heat, secondary ketone will convert into double bond. Secondary alcohol will convert into ketone. But here this is tertiary, this is tertiary. Since both of them are tertiary, you will get an alkene form. So this is the C. Okay. But if at all you treat that with NaAOI, right, which is iodoform reaction. Iodoform reaction here, nothing, this side nothing can be done because this is the compound B. From here to here we need to come. So this side we can make an iodoform formation. So this methyl will convert into an iodoform, and these alcohols will not get into any reaction. So they will remain the same, because at tertiary alcohols we cannot make an iodoform reaction. It has to be either secondary, correct, or primary. It cannot be on the tertiary position. So therefore, this is a final product we will get, and CHI3. Clear? Tough questions, but you have to learn this. Got it? All four were very, very good JEE advanced questions. So these kind of cases, the first two cases here, right? These one, two, three, four, right? Then 5, 6, 7. So these 7 cases, all PYQ cases, please learn it properly. Okay. Hmm. Next, alpha keto acids. So this is an acid, and here we next carbon itself is keto form. Then on adding with concentrated H2SO4, you will get this into an acid form. So basically, this carbon will convert into carbon monoxide, and this R minus will attack here to convert back into acid. Okay. Same goes with concentrated H plus here also. This pH minus will go here and CO will be left from this end. That's how what you will notice in concentrated H2SO4. Next, this is a very, very important reaction, which is using carboxylic salts, calcium salts, or barium salts to convert them into ketones. Suppose if you have 2 moles of this acid and react with calcium hydroxide. Okay. So then this acid will convert into a calcium salt first. So this is the calcium salt what you will get. From there, you are making a dry distillation. Okay. On dry distillation, you will convert this into a ketone. Now, how does this work? Let me show you the mechanism here. Okay. Suppose I have something like R CH3 C double bond O minus, CH3 C double bond O minus, and calcium 2 plus. Okay. Then we have this carbon dioxide and this calcium oxide. Both of them will connect with each other on heating and convert themselves into calcium carbonate. So what is left now? What is left is this will become CH3 minus, and another thing what is left is CH3, C double bond O is left with plus charge. So this will connect here and converts that into a keto form. So C double bond O, CH3. You got it? And calcium oxide actually on heating will convert into calcium carbonate will convert into calcium oxide and carbon dioxide. So this is the product that you will report. This is the significance of dry distillation. Girls, clear? Right.
Yes, sir.
So right. So you notice that on dry distillation, one of the carbon dioxide you have to remove. For the second carbon dioxide, you just have to connect with the first carbon R group, alkyl group. Done. Suppose if you have two different acid salts, I have a calcium formate also, and I have a calcium, some carboxylate also. In that case, if we perform dry distillation, first, this will give you self dry distillation. So which means you'll get RC double bond O R. This and this will give you a cross dry distillation. So you'll get this one as HC double bond O plus, and this R minus can connect. So that's how you'll get an aldehyde. This itself can form into a dry distillation, self dry distillation. So that will form into an aldehyde. And lastly, you'll have calcium carbonate here. Got it? Clear? Right. Same way here, calcium carbonate with this one will come out as calcium carbonate, and this minus charge will attack here. You will get this 5-membered ring. Here, this carbon dioxide, calcium, and oxygen will leave. So this C minus will attack here. You will get a 3-membered ring. Done? Any doubt here? Very good. So now notice another similar question where you will have a uh, uh, acid formation here. Okay, and then dry distillation is happening. Check. So first, you have CO2 and CO2 at this position. You are heating it. Okay. So here you can see 1, 2, 3, 4, 5, and then there is one CO2 will be left. So this carbon will attack here, converts into a 6-membered ring. This is the keto form which you will get. Then zinc mercury amalgam will make this keto form into alkane. That is A. And then when you will take C double bond OCl in the presence of AlCl3, at this position you can make acylation. So one acylation will happen on this end, one acylation will happen on this end. Both side you will get C double bond O, C double bond O. Then you are performing lithium aluminum hydride. So that means this will convert into alcohol, this will convert into an alcohol. And that on hydrolysis will give you C. This is a pinacolone rearrangement, if you recall, right? So from here, hydrogen will shift, right? This water will go away and this will convert into a keto form. And that's how you will get a keto form here. And from this is D, and thereafter using this is Wolff-Kishner reduction. Wolff-Kishner reduction will make a keto into alkane. So that's how you'll get an alkane. So this is a final product. Again, very difficult to, get these options. But yes, this requires a practice. This is an important question again about decarboxylation, about acylation. So you can see now how intermix questions can come. Hmm? Okay, beta? Right. Shall we go ahead?
Yes, sir.
See the next. Yeah? Yeah, any doubt, beta? Right. MnO2. MnO2 is very similar to that of calcium salt formation. So that means if you have two acids, when you react with MnO, first you will get the same kind of salt. We will get this as HCOO twice manganese salt, and this on heating will convert into HC double bond O. Just as dry distillation, again it will become MnCO3, and MnCO3 is unstable. It will again oxidize, it will get decomposed back to MnO and CO2. So this is how you will get the product. Got it? Finished? One second. So check here. Next one, same thing. If you take these two acids, we can have one self dry distillation. This one is a self, the other one is a cross. So these are the three forms you can get. Clear, beta? Suppose if you have a triether here, so OET, OET like this, and then you are reacting with RMGX. Here also RMGX will connect, one OET will come out. And thereafter on hydrolysis, it will convert into a keto form, right? You can see the mechanism. R minus will connect, OET will go away. The next mole, when you hydrolyze, this will come out as alcohol. Here it will push, converts into an ester. Ester on hydrolysis will convert back into keto form. Correct? Sorry, this is not an ester. I mean, this is like ether form, which will convert back into keto form here. Done. Next, what is Rosenmund reduction? Well, if you have an acid chloride, you react with H2 in the presence of palladium barium sulfate. Hmm. In that case, this hydrogen will attack here, removing out this chlorine, so that will convert into an aldehyde form. This is called Lindlar's catalyst. It will be always giving you aldehydes. Further reduction is not going to take place. And to make sure further reduction is not happening, we use sulfur or quinoline and add it on the surface of the metal so that it will act like a poison. Okay. Hmm. If by chance I have an acid chloride and a keto group, alkyne group, the alkyne will convert into a cis form, right? Because you know that there will be a cis addition in the presence of palladium barium sulfate, and acid chloride will convert into an aldehyde form. Okay, right. Now, next, notice what is Etard reaction. Suppose if you have, you know, toluene form here and you're reacting with chromyl chloride in the presence of CS2 and hydrolysis, you will get an aldehyde form here. Okay, see the mechanism is something like this, where you have aldehyde, we have a toluene which will have a hyperconjugation, isn't it? So due to hyperconjugation, here you will have a delta, I mean complete positive charge here, and carbon will show a double bond character here like this. This is the hyperconjugated structure, correct? And whenever there is a hyperconjugated structure, the oxygen present on chromyl chloride will accept this H plus like this. Cr, C double bond O, C double bond O, Cl and Cl. So what happens? This lone pair will take away H plus, and this will become now chromium is getting positive charge. When chromium gets positive charge, right, then this carbon which is having a pi bond here will attack on this chromium. Clear? Sorry, not on chromium. Sorry, here like this. This will attack on this oxygen, which is making a double bonded form here, so that This electrons can move towards chromium. So what happens here? So you will see carbon is making a bond with oxygen this way. And this will happen two times. Two hydrogens will be connected like this. Okay. So one will become this one. The other one will become OH and OH. This one is going to be OH here and OH here. Okay. So as it goes, you can see there are two chlorines here. So one of the chlorine will come out as you make the reaction. So that means as this lone pair will come, Cl will come out. Here also lone pair will make a double bond, Cl will come out. That's why I have written that directly. Okay. Right. So let me take it back to that part like this. Okay. Now this compound, once you get this on hydrolysis, will remove out this part and gets two OH groups. And two OH groups will convert into an aldehyde form. Done. The same logic is applied even if you take a chromic anhydride, that is CrO3. CrO3 on hydrolysis will convert this part of carbon into an aldehyde. So this is benzaldehyde, this is benzaldehyde form. Yeah? So this is etard reaction. Clear? Next. Next is Gilman's reagent. RC double bond of Cl in the presence of Gilman's reagent will convert that into a keto form. Okay. Gilman's reagent is like this, R2CuLi. So this R minus will attack here, Cl will go away, and that's how you'll generate a keto form. The same can be done even with R2CD, R2Li. So all these will have very, very similar reaction. Okay. So they all will be able to prepare the keto forms. Next. Check out Dibal H. Dibal H does not make any reaction with acid. So this is a very poor yield. As per J, we do not make this reaction happen. But cyanides, esters, acid chlorides, everything will give you aldehydes. This we discussed in alcohols already. So do remember dibal H. Alternative dibal H, we have this another part. This is trimethyl carboxy aluminum hydride. Okay, so lithium tetra butoxy aluminum hydride. Okay. Now LTBH, just like dibal H, this is LTBH. This will also give this H minus, remove this Cl minus, end up getting aldehydes. Wacker process. Wacker process is using PdCl2 in the presence of O2. So basically, O2 with with some water will convert into OH minus and H plus. So you remember this, like palladium is getting reduced here and aldehyde is getting, alkene is getting oxidized. So one part will take H plus, the other part will take OH, correct? But here it is like an substitution. So here this hydrogen is removed, this hydrogen is removed, and you are only substituting. Instead of this, you are putting OH, and here also you are putting H. So what are we getting? The substituted form, which is enol form, like this. You'll have this as an enol form. That is OH double bond CH2, and that converts into this keto form. This is called Wacker process. Oxo process, you can take carbon monoxide plus H2 and make something like a Markovnikov addition. So that means from here pi bond you attack on this one, H minus will attack on this plus. Okay, and that's how you'll get an aldehyde form. So this is a Wacker process. This is an Oxo process. In both these cases, we are getting an aldehyde form. I mean ketone and aldehyde form. Right. Next, we will come back to this reaction. As of now, it's not required. Correct. Now, whatever we discussed so far, these are all the preparation reactions of aldehydes and ketones. Hmm. Now let us focus on the chemical reactions. Correct. So when it comes to aldehydes and ketones, what are the main chemical reactions? It is nucleophilic addition reactions. Aldehydes and ketones mainly participate in nucleophilic addition reactions. Okay. The first reaction includes HCN. Okay. I think I forgot to write some theory here. One second. I'll do one thing. I'll just push this part little up and write some theory here, but okay. That part is missing out. Hmm. See, what is the theory, important theory here? Check it out. See, when it comes to aldehydes and ketones, this is a typical structure what you have. If this is an angle theta and this is, sorry, alpha and beta here, so this is alpha and this is beta, usually beta is greater than alpha. This is the bond angle form. Okay, right? Which means if at all I take it as a plane here, right? So if at all I take it as a plane here like this, then carbon is here, two other groups are here, then double bond O is here like this. Okay, this is a planar structure, isn't it? But if you notice its orbitals, right, where exactly the orbitals are present, you will notice one orbital is above the plane like this, the other one is below the plane. Here also one orbital is above the plane, the other one is below the plane, this way, correct? Hmm? This is a pi bond, correct? And now what happens, uh, because the oxygen is more electronegative, because of its more electronegative, the electron density is always more found towards oxygen. So because the electron density is more here, now the shape of the orbital will look something like this. Will be the shape of the orbital. Below also, you will see the shape like this. Got it? This is the shape of the orbital. Correct? So which suggests that most of the electron density is towards the oxygen end. So this is how the electron density is present on the oxygen end. So which leaves behind carbon with high delta positive charge. So it will have high delta positive charge. This will have high delta negative charge. Okay, clear guys? Right. And that invites the nucleophile to attack either from here, or nucleophile can go and attack from here, from the top. So nucleophile can go and attack from the top. Done. This is the way the attack is possible. Understood? So there are two reasons of reactivity of nucleophile. Let me write down two reasons for nucleophilic addition reaction. The first reason being, okay, high polarity, high polarity between carbon and oxygen. Correct? Now, second thing, this is about high polarity. What is the second part? Second part is, you know, least, what do you say, planarity. Planarity on carbon. Okay, because it is planar, from the top, it will be exposed to attack. Okay, now the rate depends upon whichever will give you more high polarity and whichever will give you more planarity. Suppose if these alkyl groups are bulkier, then they will hinder nucleophile to attack, correct? So therefore, rate of the reaction, so rate of nucleophilic addition reaction directly proportional to first polarity of C double bond O, right? And it is inversely proportional to uh, hindrance hindrance on C double bond O. So these groups. So if they become bulkier, if these two groups become bulkier, now it will start hindering more. Got it? So if at all I check out the reactivity order. So HCHO will be most reactive. then CH3CHO, then CH3 CH2CHO, then phenyl CHO. Because phenyl, what happens due to its resonance, it will decrease the polarity on carbon. But here is an interesting fact. After this, then starts the ketone. Till that time, ketones will not start only. So then further more substituted ketones like this. And as you can see, as many more substitutions as possible, it will become less reactive. But again, if you have a benzene directly connected, the reactivity drastically decreases. And finally, if you have ketone group with both the sides being benzene, that is a least reactive part. So this is the reactivity order. Done. Girls clear beta? Right. Next, in case if you have any nucleophile and electrophile approaches, two mechanisms. First, acid catalyzed mechanism. Acid catalyzed mechanism. What does that mean? Suppose if you have a ketone like this, and then I have H plus, and thereafter a nucleophile is present. Then first the lone pair will take H plus. Sorry, I meant to say nucleophile is present here only, but H plus is present in this case. So nuclear first oxygen will take away that H plus, gets into OH plus formation, and that activates the delta positive charge on carbon further, and the nucleophile will attack. And remember, whenever the nucleophile is attacking, that is always going to be the slow step. This will be the slow step. So this is the rate determining step. Now, suppose if there is a base catalyzed or base uh, catalyzed form, how does it be? Directly, if you have a nucleophile which is stronger, so usually base catalyzed means we expect the nucleophile is stronger here. So that is the one which will attack directly the carbon part. This bond will break, and you will get this as O minus and Nu, and this itself is a rate determining step. And thereafter, when you react with water, then you will get this as OH and nucleophile. Clear? So remember, this is the basic idea behind how the reaction takes place. So what did you notice? See, whether you take acid catalyzed mechanism, base catalyzed mechanism, in either of the cases, the nucleophilic addition is always the rate determining step. Is that clear? That's the reason why we call it as NAR. Irrespective of acid catalyzed or base catalyzed, we still call it as NAR. Why? Because nucleophile is getting added in the slowest step. Okay, right? Please go through it once. Please do ask if you have any doubt in that. Then I can go ahead. Right, shall we go ahead? Any doubt? मैं दिया. चलो, let's see. Now let's see all the nucleophilic addition reactions, starting with HCl. Okay. So first, if you take an aldehyde, react with HCN in the presence of KCl. Why KCN is required? Because here HCN is a very weak acid. It will not give sufficient amount of cyanide on it. Okay. So that's why we add some amount of Cn minus. So this Cn minus will attack on carbon, gets an O minus, and that O minus will take H plus from HCN, and that's how the reaction will take place. So this is more like the second type of mechanism, isn't it? This is more as a second type of mechanism. Acha, if you do not put KCN, then it will go with the first type of mechanism. Correct? So first H plus is getting added. After that, Cn minus will get added. Okay. Correct. So I think the reaction is clear. Now, what has been noticed is that this the formation which is cyanohydrin, correct? This is called cyanohydrin, and cyanohydrin formation is a reversible form. That means the cyanide from here can actually take H plus, push this double bond, remove that as Cn minus. Okay, that will remove it as Cn minus. So that's how you will get the reaction back into aldehyde formation. Clear? Now every aldehyde and ketone will give this reaction. Okay, every aldehyde and ketone will give this reaction. That includes basic anything RCHO, PCHO, and P double bond of CH3, which will not give the reaction here. See, which will not give the reaction. The reaction is not given by, see, the reaction is not given by dimethyl ketone, sorry, diphenyl ketone, like this. Okay, and you have phenyl on one end and all three bonds on the other end. Now, these two will not give the reaction. Remember, more than which is giving, always remember which is not giving. It is easier to remember. Okay. So if an integer type is asked, like which of the following will give the reaction or not, so make sure that you neglect these two. Rest of them will give the reaction. Okay. Now this one I told you, right? Which one is more reactive? Of course, if you have more than aldehyde, here I started off with formaldehyde. See, here I started off with formaldehyde. But on that formaldehyde carbon, if there is a withdrawing group like CF3CHO, CCl3CHO, that will make it even more reactive. Okay. And if both side also, if there is CF3, that will become even more reactive as well. So 1, 2, 3, these will dominate. Then comes aldehyde of all the kinds, all the way up to this position, which I told you already. Yeah. Right. Second reaction is sodium hydrogen sulfate. Notice aldehyde, if you have RCHO and react with HSO3 minus. Okay. So in SHO3 minus, you will notice that we will have sulfur with a lone pair. Let me write the structure. S with a lone pair, double bond O, sorry, O minus, and OH. This is the structure we have. Okay. HSO3 minus. So it is this lone pair of sulfur which will attack on carbon. And as it attacks, you will get this as O minus and you will get this sulfonyl form. And then you take H plus in from water or from acidic source. If you take it from water or acidic source, clear, then you will be able to get this OH and convert that into white PPT. So this is what you will get as white PPT form. Okay. Right. So this white PPT, if you add it with basic medium, it will become Na2SO3, SO2 will go away, and you will get this as aldehydes. In acidic medium also, it will become RCHO, SO2 will go away, and NaCl will form. Done. So that's how you will see aldehyde in both the cases. Yeah. This is being used as a very important reaction for separation process. इसको मैं as an example यहाँ पे लिख देता हूँ. Okay, separation. Suppose I have an aldehyde beta and I have an alcohol. अब हमको ये दोनों separate करना है. You got to separate these two. So what you can do? You can first use sodium, hydrogen, sulfide. Okay. So by that you will see this will become RCHOH SO3 minus Na plus, which is a precipitate, and RCH2OH will remain, no reaction with this aldehyde, alcohol. So now what you will do, you filtrate. So you make a filtration process. Due to filtration process, you know, the precipitate which is there, this precipitate will be separated out. This precipitate will be separated out. And on the other side, we will have an alcohol form. This is the liquid form which you will have, correct? And this part, this part which is a precipitate, if you react with HCl again, it will become again an aldehyde part. Okay, and you can see aldehyde and alcohol both got separated out. Done. This is a separation method used to separate aldehydes and alcohols. Okay, I guess this part is clear. Right. Now, because the thiosulfate, this one H, sorry, hydrogen sulfate is a uh, bulkier nucleophile. It is bulkier nucleophile. Not all the aldehydes will make a reaction. Okay, not all the aldehydes will make reaction, and that's what you will notice. If you have uh, generally any methyl ketones and aldehydes, methyl ketones and aldehydes only, methyl ketones and aldehydes, only these two will make a reaction. Okay, methyl ketone and aldehydes. Okay, so you can see methyl ketone, aldehydes will make reaction. What will not make the reaction happen? See, if you have a phenyl group with CH3, although this is methyl ketone, this will not give positive test. In case if you have a tert butyl on one side also, that will not give a positive test. Then if you have two ethyl groups, isopropyl groups, tert butyl group, all of them will give negative test for NHSO3. It's a very, very important test, guys. Okay, this explains, this test will explain uh, you know, which groups are methyl ketones or aldehydes and which of them cannot react. Okay. Next, reaction with water. What happens in acidic aqueous solution? And so check. If you have an aldehyde reacts with H plus, you will get hydrate of carbonyl group. You will get a hydrate of carbonyl. What is a hydrate of carbonyl group? You will have CH, sorry, like this, C double bond O and H we have. So as the H plus will add on to it, so you will get this as a double bond OH plus. So this is the protonation that takes place, and thereafter water as a nucleophile will attack on this position, pi bond will move, and that's how you will get RCH with OH and OH. So that's how we can get two OH groups. So these two OH groups existing is called as hydrate. Generally speaking, hydrates are not stable. The reaction will always go in the backward direction. Got it? Clear? But there are certain hydrates which are very stable. Certain hydrates which are very stable. Clear? Which of those hydrates? See, first one, chloral. CCl3CHO. This is called chloral. Okay. Chloral on hydrolysis, this aldehyde will convert into OH and OH. And the chlorine from the other carbon will make a hydrogen bonding with it. Okay. Chlorine from the other carbon will make hydrogen bonding on it. Clear? Now, is there any other group? Yes. See this one. Cyclopropane. You can see cyclopropanone. So the C double bond O will convert into OH and OH. So that's how we can get this into hydrate form. Why this would be very stable hydrate? Why this one is very stable hydrate? Here this is stable hydrate because here it was sp2 hybridized carbon. Here it is sp3 hybridized carbon. So what happened? Uh, Angle strain got released. Angle strain released. Okay. So you can see. So sp3 is better than sp2 because sp2 it has to maintain 120 but it is maintaining 60. Here it has to maintain 109 degrees. So it is less angle, right? So the strain is less. Got it? And now this is called ninhydrin. This is ninhydrin. So you can see ninhydrin on hydrolysis will make this particular oxygen as OH and OH. So when it becomes OH and OH, the adjacent oxygen will make a hydrogen bonding. And because of that hydrogen bonding, this is very stable hydrate. So this is a stable hydrate. Another form which makes it a stable hydrate is three continuous keto groups like this. If you have three continuous keto groups, you could imagine this way. You can have double bond O, and the center carbon will make it as hydrate, OH and OH. And here we have pH and pH. So these two will make an attraction. So that's how the hydrogen bonding is. So this will be a stable hydrate. So you can see this is stable hydrate. Done?
So,
Yes, beta.
second case, where did like only one get,
Huh?
where did only one group get hydrolyzed and not the other two?
Pardon, say it again. This one.
Yes, sir. Why did only one of them get hydrolyzed and not the other two?
See, what we are doing is we are doing hydrolysis H3O plus. Okay. On hydrolysis, this carbon is taking OH and OH. I mean, this carbon is becoming OH and OH. The reason why it is becoming is because it can make a hydrogen bonding on both sides. That cannot be made on this ketone or this ketone, right? So which ketone is more ready to react? This ketone is ready to react. Okay.
Yes, sir.
Is that your question?
Just said that, but can't like all three of them have the
See,
OH
beta.
group then?
No, no. If all three of them, how will they make hydrogen bonding?
Right. Okay.
If you
Got
have
it.
this oxygen, then it can make a cyclic structure this way and make a hydrogen bonding. 5-membered ring. Here also it will become a 5-membered ring and hydrogen bonding. Okay. Mm.
Yes, sir.
Done? Mm. Right. Now, this is their respective K equilibrium value uh, for the formation of hydrate. Okay. This is hydrate equilibrium. Got it? Clear? So you can notice that CF3, COCF3 has the highest amount of K equilibrium. Of course, it has to be because it can make a very strong bonding. Hmm? Done?
Yes,
Next.
sir.
Notice reaction with ammonia. Okay, ammonia and ammonia derivatives. Okay, what does that mean? Suppose if you have an aldehyde react with ammonia in H plus. Okay, if you do that in H plus here, That means this has to be mild acidic medium. Then the ammonia will attack on carbon and water will come out of it. So what is left now? Imines are left. Okay, correct. So you can see aldehyde with RNH2. Now again this H2 and this oxygen will go away. What I'll just show the mechanism how it operates. See C double bond O OH plus. That is first taking H plus. Then ammonia, the lone pair from here will attack. Pi will be moved out. So we will get this as OH and NH2 plus. And lone pair on oxygen will take H plus internally, convert into OH2 plus, which is a better leaving group now. So now this NH will make a double bond form here. Okay, so this is NH3. Okay, so as it makes a double bond form here, this bond will move away and you'll get double bond NH2 plus. And since you are using in acidic medium, the H plus is lost from here and you will get this as NH. You got this point now? How the mechanism is taking place? Right. Same way. This is the same mechanism. Now, instead of H, you can have some R group. That's all. Instead of H, you can have any R group now. So if you have it any R group, then this H2 and oxygen both can dehydrate to convert into this imines. Okay. So these imines are Schiff bases. I mean, they are called as Schiff bases. So don't worry about the terminology yet. And if at all we reduce this double bond, it will convert into a secondary amine. Do you recall the reagents? These were all the reducing agents which we discussed. Lithium aluminum hydride, NaBH4, nickel and H2, ethanol. This is Bowold blank reduction, red phosphorus Hi, uh, Clemenson's reduction, Wolff-Kishner reduction. Everything will convert these imines into amines. Right. Next. What if you have a secondary group? In case if you have a secondary amine, then instead of removing H2O from two hydrogens here and one oxygen here, now the easier way is think this way. For that ketone, I will write the enol form. This is enol form. And then for this amine, I will write it this way. This is the secondary amine. Now what you do, you remove this water. So this is how you dehydrate. Then join both of them. Now as you join, we have a double bond here, N connected with this group. So this is an ene plus an amine. That's why it is called enamine. This compound is called enamine. I hope you got an idea how the mechanism is. Right. Now, instead of this Z group, right? So that means instead of this R group could be any of this. And based on that, what is the product you will get? That is what we have figured out now. Check out. Suppose if you have, instead of that R, you have OH. So that means, what is the reactant in this case here, beta? The reactant is NH2 like this with OH. This is the reactant. Here it is NH2 with NH2. Here we have NH2 with NH and pH. So I hope you got this. So we are talking about this particular group here. That is remaining, right? That's not reacting. So therefore, so as it reacts with that aldehyde, you will get first, you remove that, you will get C double bond N with that OH group. Now this functional group is called oxime. C double bond N with an OH group, that is called oxime. Okay. Any doubt? Right. Next. Similarly, if you have NH2 here, then this is called hydrazone. So how does the hydrazone looks like? It will be RCH double bond N with NH2. This is hydrazone. Now instead of we have a phenyl, then we call it as a phenyl hydrazone. If you have NH, then C double bond or NH2, an amide group is there. If you have an amide group, it is called semi-carbazide. The name is semi-carbazide, and ide will become one. Ide will become odd. So this will be carbazone. So this is the connection we have. Next, if you have this entire group, so there is a phenyl with 2,4-dinitro. So that's why it is called 2,4-dinitrophenylhydrazine, and its name is Brady's reagent. The compound's name is Brady's reagent. That would give us 2,4-dinitrophenylhydrazone. Like I said, ine, anything ine, ide, they will become one. So this will become phenylhydrazone. So this is the structure of phenylhydrazone, 2,4-dinitrophenylhydrazone. Okay. Now what you would notice here is most of these, right? For example, phenylhydrazone. Okay. Then oxime. Correct. Then 2,4-DNP. These are colored compounds which can be easily crystallized. And that's why 2,4-DNP is used as a test for aldehydes and ketones. If at all there is an aldehyde and ketone, then on treating with 2,4-DNP, which is a colorless liquid, after the reaction it will become a colored crystal. So if you are able to generate some colored crystals, that means we are talking about aldehydes and ketones presence. Okay. Right. Now you can see formaldehyde. Formaldehyde, when you react with ammonia, the first mole that will form is CH2, I mean CH2 double bond NH. This is what you will get. But this is highly unstable. So this will keep further reacting. This is a highly unstable form. So it will keep further reacting. And as it starts reacting, what happens? This pi will go attack on the next carbon's aldehyde. So which is H, like this. HC double bond OH. So from this here itself, the pi will attack. If we keep on doing that, we require at least 4 moles of ammonia and 6 moles of formaldehyde, like this, so that it can become this cyclic structure. Okay. So this is called as hexamethyl tetraamine. Of course, there are 6 methyl groups and 4 amine groups. And the industrial name for that is erythropine. This is called erythropine. Okay. So please do remember the structure, how it looks like. Okay. So this is erythropine. Next, in case if you have two ammonia groups here like this and reacting with an aldehyde, okay, for benzaldehyde. So you can see that H2O can go from here, H2O can go from here, and H2O can go from here. So what are we getting? You will get this form. So 3 moles of aldehyde can connect this way. Okay. Hmm. Next, if you have 3 moles of aldehyde and 3 moles of ammonia, you can actually get a cyclic structure like this. Are all the cases clear, beta? Please check the ammonia cases once, all of them. What is the product you will get? Check that. See the next reaction with alcohols, right? If you have an aldehyde, react with 2 moles of alcohols in dry HCl, which means there should not be any water content in it. So lone pair from oxygen will take H plus. You will convert into this form, and the first mole of alcohol can connect onto this carbon. Pi bond can shift, and you will get an OH and OR dash. Now this is called hemiacetal. This is called hemiacetal, and hemiacetals are highly unstable. So to make sure the reaction further goes in the forward direction, you have to take excess of alcohol or at least 2 moles of alcohols. Okay. So as you push it further, this hemiacetal can also get protonated. It will become OH2 and leave, and that's when the second mole of water molecule can attack. So eventually that will form OR dash and OR dash. This is called acetal. Okay, what are we getting? We are getting hemiacetal and acetal form. Girls clear beta? Right. Now notice hemiacetals are highly unstable in both acidic and basic medium. They will immediately try to retract back to aldehydes. Okay, whether you keep it in acidic medium or basic medium. Acetals, on the other hand, are stable in basic medium but unstable in acidic medium. But unstable in acidic medium. Right. So this is what we need to know. Acetals are being unstable in acidic medium. Clear? Check. So if you have a ketone, react with 2 moles of alcohol and dry HCl. So you will get this as OR dash and OR dash. This is acetal form. If you have a if you have a diol on the same molecule, so one oxygen from here, another oxygen from here will attack and make a cyclic structure. And this is called cyclic acetal. This is called cyclic acetal. Suppose if you have two keto groups here, and I take dry HCl. One of the keto group is masked. This is called masking. Masking of keto group. Keto or aldehyde group. Then now when you use lithium aluminum hydride, it will only reduce this part of the ketone. So that will convert into alcohol. NaBH4 also converts only this part of ketone. NaNH2 and KOH only convert this part of ketone into alkanes. Yeah. And then when you do hydrolysis, this bond will break and converts this into double bond O. So double bond or double. So what happened? We restored that keto form again, correct? So if you want to get the keto form back, right, and till the time the reaction is happening, you just want to mask it, right? You just want to protect it. So then this glycol will act like a protecting group. So it will protect that aldehyde or a ketone, whichever you want, and the rest of the part can be sent into reduction reactions. Clear? So there are a lot of questions based on acetal and hemiacetal forms. Okay. So that we can see it in the next class how that will operate. Clear? But this is the first part of aldehydes and ketones beta, which includes first set of reactions as well as preparations. Okay.